Alright, so we're going to talk about the inverse. So this is the last section of chapter 1. Okay, so there's lots to know about the inverse, and we're going to kind of write it all down, and then we're going to go through and we're going to look at it. Alright, so first of all, when you talk about the inverse, it's written as the inverse of f of x. So it's like this little -1 power, it looks like. Okay, so that means the inverse of f of x. So inverse, let's say inverse function of f is formed by undoing the function. In order to undo it, you have to interchange the x and y in an equation, then solve for y. So y then will become equal to the inverse of f of x. So that's how you find the inverse. You have to interchange the x and the y, and then you basically have to resolve the equation for y. Okay? But tons of cool stuff happen when you do that. So the first thing is that it interchanges the domain and range. Okay? If point AB lies on f of x, then BA will lie on the inverse of f of x. So what that's telling you is that xy now will become yx. They'll flip-flop. Okay? If two functions are inverses of each other, then f of the inverse of x will equal the inverse of f of x. And both of those will simplify to x. Lots of notation there. Let me explain what that means once you write that down. Okay, do you notice that these are compositions? One of them you're plugging the inverse into the original, and one of them you're taking the original and plugging it into the inverse. When you do that, when you simplify them after you do the composition, they'll both simplify to x. That's how you know they're inverses of each other. Okay? If f of x and the inverse of f of x are graphed, then they are a reflection over the line y equals x. Okay, so we're going to take a look at all of these pieces once we kind of get into the problem, but this is all of the cool stuff that happens with the inverse. Alright. We're going to talk about the horizontal line test now. Okay, so this is how you determine if something is one-to-one versus many-to-one. Alright, so we're just going to kind of create a table here to compare. Okay, so to be one-to-one, only one x for every y. Okay, so if we take a look at this, let's say we had the graph of y equals x cubed. Okay, or f of x equals x cubed. If I was to plug in a value for x, I should only get out, 1y here. So, or if I plug in a value for y, I should only be able to get 1x. So if you think about like f of x equals 1, isn't that telling you that y equals 1 here, that notation? Right? This is saying take that function, x cubed, and set it equal to 1. So when I do that and I take the cube root of both sides, I just get x equals 1. I only get one value for every y. Now, an easier way to look at this would be to do the horizontal line test. And the horizontal line test is the same exact thing as the vertical line test in the sense that if it only hits at one point, then it's 1 to 1. Okay? The only difference is you draw a horizontal line. So if I was to draw a horizontal line anywhere on this graph, I would only touch at one point. That's how you know this is 1 to 1. Now, why do we want to know if something's 1 to 1? Well, if something's 1 to 1, then it'll have an inverse. Okay, that's the key there. So if function is 1 to 1, then it has an inverse. All right, so now let's look at many to 1. So many to 1, there are 2 or more x's for every y. So if you think about like f of x equals x squared, and I do the same thing. I let f of x equal 1. And I set this x squared equal to 1, and I solve for x. When you take the square root, don't you get plus or minus? So this is saying for that one y value, you could plug in either positive 1 or negative 1 and get out the same result. And now if you think about the graph, right, y equals x squared is a parabola. If I were to do the horizontal line test and draw a horizontal line anywhere on that graph, I would be touching more than one point, therefore making it many to 1. Now, if function is many to 1, then no inverse. Hi. Thanks. Okay, so can you just maybe make yourself a note here? We're really doing the horizontal line test. And the reason why we do that, the reason why we want to know if something's 1 to 1 or many to 1 is to determine if something has an inverse. Okay? So now we're going to actually do some examples. So this is the fun part. This wasn't the fun part, but now the fun part's coming, in case you weren't sure. Okay, so let's do this. Find the inverse algebraically. I guess I should have said this before I started writing. You're going to need quite a bit of space for this problem. So if you're like at the end of the paper, if you have like a third of a page, you should be okay. And then graph. Okay, so let's start out easy. Let's start out with f of x equals 3x plus 2. Okay, so the first thing they want us to do is they want us to find the inverse algebraically. So the first thing you have to do is you have to plug in y for f of x. So everyone agree that f of x is the same as y. Okay, so I'm going to get rid of my function notation. I'm going to replace that with y. Then it says you have to interchange the x and the y values and then resolve the equation. Okay, so that's what we're going to do next. I'm going to make this x and this 3y plus 2. All you do is interchange your x and y. Now this is a linear equation, so it should be really easy to solve, right? So we're going to subtract the 2, divide by 3. So now I have y equals x minus 2 over 3, or, 1/3 x minus 2/3. Once you've gotten here, once you've resolved for y, this is now your inverse, and you need to write it back into function notation, letting the reader know that this is an inverse. So you write the inverse of f of x equals x minus 2 over 3. Okay, so this is the first part. Everyone okay with that? Okay, now what we're going to do is graph this. Okay, so now when you're graphing, I know it's a line, okay, so I know it's super easy to graph, but just for fun, we're going to make a table, okay? So we're going to make a table for f of x, and that was 3x plus 2, and we're going to make a table for the inverse of f of x, which was x minus 2 over 3. Let's just go ahead. This looks great. Okay, so now I think you know how to make a table, but we'll just go through it just in case. All right, so let's say I'm making the table for f of x. Then, I don't know, let's just plug in values like -2, -1, 0, 1, and 2. Okay, when I plug in -2, I get out a -4. And then -1 is going to give me -1, 0 will give me 2. Notice I'm going up by 3 every time because that is my slope, right? Okay, now, let's make a table for the inverse of f of x. I'm going to give us some values just arbitrarily, okay? So let's say we plug in a -4, for example, okay? So if I plug in a -4 here, I have -4 minus 2, which is -6, divided by 3 gives me -2. Agree? Okay, let's say I plug in a -1 now. So if I plug in a -1, I have -3 divided by 3, so I get -1. Let's go for a 2 next. If I plug in a 2, what do I get? 0. While we're at it, let's do a 5. So 5 minus 2 is 3. 3 divided by 3 gives me a 1. Anyone guess the next value? Oh, 8. Yeah, I agree. Let's try 8. So 8 minus 2 is 6. 6 divided by 3 is 2. Can you take a look at what just happened to the tables? What happened? They flipped, right? Because we said that with the inverse, if AB lies on f of x, then BA is going to lie on the inverse. So do you see that once you've made one table, you literally don't make the second one. You just flip everything because you know you found the inverse. That's cool, right? Exactly. Okay. We're going to graph it now. Okay, so now we're going to see some more cool stuff. Okay, so go ahead and graph f of x. Oh. And then make sure you label that like f of x and the inverse. If we had graph paper, this would probably look a lot better. All right, so take a look at my graph. I added in an extra line, y equals x. Do you see here that f of x can reflect over that y equals x line to create the inverse? Every time you graph these, you should be able to see that. You should be able to see the reflection because, again, if you go back to what we talked about, we always see these being reflections over that y equals x line. So it's a good way to verify that your graph is correct. Okay? Everyone okay with that? All right, so now we're going to do another part of this problem. So this problem is done based on what we've been asked to do, but we're going to throw in example 2 here. And now we're going to verify that f of x and g of x are inverses of each other. And let's say that f of x equals 3x plus 2 and g of x equals x minus 2 over 3. Now, if you'll notice, those are those two functions we just came up with. But we're just going to kind of verify that they're inverses of each other. So, when I ask you to do this, there's really two ways to do it, but there's one way that I want you to do it, okay? So this is the way that you're going to do it, and you have to show it both ways. So if you go back to what we talked about, if two functions are inverses of each other, then their compositions have to be simplified to x. So what we're going to do is we're going to find their compositions. So I'm going to find f of g of x, and then I'm going to find g of f of x. And if I can show that they both simplify to x, then I've shown that they're inverses of each other. So this is like proving it, okay? So remember, to find f of g of x, you take g and you plug it into f. So everywhere I see an x, I have to put x minus 2 over 3. So this is like what we did yesterday. So I have 3 times the quantity x minus 2 over 3 plus 2. Well, what happens here with our 3's? They cancel, and we get x minus 2 plus 2. So f of g of x equals x. Okay, now it's not enough just to do one side. You have to do the other side as well. So now we're going to do g of f of x. So now I'm going to take f of x and I'm going to plug it in everywhere I see an x in g. So those 2's cancel. I have 3x divided by 3, and then g of f of x equals x. Once you've shown that both of those are equal to x, then you've proven that they are inverses of each other. Make sense? Okay. Now it's going to have to get a little bit harder because this is just too easy. Okay? Here we go. Let's take a look at this. We're going to do the same thing we just did in example 1. So find the inverse algebraically and graph. Okay, so let's say we have f of x equals the square root of x minus 4. Okay, now, before we start going on this, I want to go back to example 1. Looking at our given function, do you agree that this is a polynomial and there's no restriction in terms of the domain and range? We haven't talked about that piece yet, and that is a huge piece of the inverse, okay? Now also, when we were looking at 3x plus 2, so just look at that line, y equals 3x plus 2. If we were to do the horizontal line test, it would be 1 to 1, right? So it had an inverse. Okay, so we got to keep that part in mind, okay? We really didn't have to talk about the domain and range here because it wasn't a factor in this problem. But now we have to take a look here. So do you agree that the square root of x minus 4 has a restriction, right? So what is the domain of the square root of x minus 4? Four to infinity, right? So I'm just going to make myself a note here. The domain is 4 to infinity. Now think about this graph. This is a graph of a square root, and it's shifted over right 4, correct? So it's sitting on the x-axis is shifted over right 4, and it goes to positive infinity. So then what is the range? What kind of answers can you get out of this? 0 to positive infinity. So I'm just going to make myself a note there, and then I'm going to worry about it in a little bit. Now, first of all, looking at the square root of x minus 4, if you think about the graph, is it 1 to 1? Right? Like, it looks like that, right? So anywhere you draw a horizontal line, we're going to be good. Okay? It's going to be 1 to 1. So we know this is going to have an inverse. All right? Okay, so here we go. So we change f of x to y. We then interchange our variables. Okay? How do I solve for y? What's the first thing I have to do? Square both sides. So I get x squared equals y minus 4, add over the 4, and I get y equals x squared plus 4. Once I've gotten y by itself, this now becomes its inverse. So now I'm going to name this the inverse of f of x equals x squared plus 4. Okay? Now I'm going to come back to the domain idea once I see the graph. I think it'll help you to visualize it a little bit better. So again, I have to make a table. I'm going to make a table for f of x, and I'm going to make a table for the inverse of f of x. Now when I make a table for my square root of x minus 4, I want to choose values that I can plug in and easily evaluate, right, since it's a square root. So if I plug in a 4, I get out 0. Let's see, the next number you'd want to plug in is, what, an 8? Okay, so if I plug in 8, I get 2. And what's the next one? 13 minus 8, or 4 gives me 9. Square root of 9 is 3. So that's good. When you're doing the square root, you don't need a ton of points, okay? So now we already looked at the fact that if they're inverses of each other, their table just interchanges. So I don't have to spend any time thinking about this table. I'm just going to write down the flip of the one I just made. Okay, I'm going to do this again just so that we can see it on the graph a little bit easier. Okay, so now let's graph this. All right, so I have 4, 0, and 8, 2. That's all I'm going to put on here. So this is f of x, which is what I thought it would look like, right? Thinking about the transformation that's happening. Okay, now when I graph this other one, I have 0, 4, 2, 8, and that should be good. And I know that it's an x squared, right? So it should be like a parabola shape. But what are you noticing about this parabola? If I take a look at the inverse here, I should see this other piece, shouldn't I? Right? If I was going to graph x squared plus 4 normally, I'd graph the entire parabola. Agree? But now, I only see half of it. Why? It's about the domain and the range. See, in order for a function to have an inverse, it has to be 1 to 1, right? But a parabola isn't 1 to 1 unless you limit the domain. So what happens here is we can still see this reflection, right? Like we can still see that it's flipping y over, or y equals x. We can see that. But what just happened here? Take a look at this graph. What's the domain of this inverse now? Look at the graph. What's the domain? Doesn't it go 0 to infinity? What's the range? 4 to infinity. Now, this is a super cool part. Take a look at these. What happened? They interchanged, right? They flipped. This domain now became this range. This range now became the domain of the inverse. That's why it stays 1 to 1. That's cool. Now, here's the thing. when you're finding the inverse algebraically and there's a restriction, which if there's a restriction at the beginning, there has to be one at the end. So once you've interchanged it, once you've actually found the original, I already know the restriction. This range has to become my restriction. So if there's a restriction at the beginning, there has to be one at the end. The final answer then for this inverse algebraically would be this. It has to include the domain. Otherwise, it's no longer one-to-one. It can't exist. So I might write that down in my notes. If there's a restriction at the beginning, then there has to be a restriction at the end. The range from the beginning is the restriction at the end. It's the domain, because they have to interchange. You can also see it from the graph. I mean, that's some pretty cool stuff. I can tell you find it very interesting. Let's think for a second. If you were to start out with this, let's say, f of x equals x squared, could you find the inverse? So if I started out with f of x equals x squared and I asked you to find the inverse, could you do it? No, because it's not one-to-one, right? If it's not one-to-one, it can't have an inverse. But now what if I put this stipulation? X is greater than or equal to 0. Isn't that giving you a restriction on the domain? Right? This is saying you can only look now at the right side, therefore makes it one-to-one. If there's a restriction at the beginning, then we got to make sure we talk about that restriction at the end. Okay? You're going to try one now. So let's say, same directions. So find the inverse algebraically and graph. Okay, so let's have f of x equals the square root of x. Okay, I want you to do all the same steps we just did. I should see tables, I should see your work for the inverse, I should see a restriction if necessary, and then the graph. And I also want you to include that y equals x line on your graph so you can see the reflection. Talk to your partner. Did they come up with the same restriction? Are your tables switching? one together here. So I will put up mine, and then we'll kind of talk it through. Okay, so again, here's a couple of things I noticed. Number one, all of you solved for this correctly. You got x squared. That's great. However, when you write your final answer, you want to make sure it says f to the negative 1 of x, the inverse of f of x. There is no longer a y. This is y now. Okay, so I saw a lot of equals y as well. So get rid of that. From the beginning, there was a restriction, right? The domain of this square root of x is from 0 to infinity. The range is from 0 to infinity. This range becomes your domain. This is the only piece you have to list. So, in terms of an answer, what am I going to be looking for? You have to give me this. If you don't give me the restriction, it's at least a 1-point deduction. Okay? If you don't write the inverse of f, it's at least a half a point of deduction. When you graph on here, do you have arrows on the ends? Do you have your f of x and your inverse of x labeled? Do you have the y equals x line labeled? All of those little things, that's what we're looking for, precision. Okay? Do you have questions? Yes?
You need the y equals x line.
Yes, I do want to see that on your graph. Okay? So you can see that reflection idea, yeah. And that's, that's a great way to check your work is if you don't want to flip this table, plug in values. See if you get out the same results. Okay? That's a good way to check your work. Do you have any other questions?